So, today we're going to go through one last integration technique. This one is called partial fraction decomposition. So this one, section 7.4, is called integration of rational functions by partial fractions. Okay? So, first of all, we should talk about what is a rational function. Well, a rational function is just a ratio of two polynomials. You probably remember what a polynomial is, but just in case you forgot, let's just go ahead and define that right now. So a polynomial is just any function that takes the form f of x equals cn x to the n plus cn minus 1 x to the n minus 1 plus dot 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 all the way up to c1x plus c0, where c0, c1, dot 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 all the way up to cn minus 1 and cn are real numbers. Okay? So you just take successive integer powers of x, multiply them by a bunch of constants, and then add that all up. And that's a polynomial. Okay? And the degree of the polynomial so the degree of f, well, that would be the largest exponent that you get when you write out the polynomial. So we'd say is the value n, provided that Cn is not 0. Okay. So the exponents, so the largest exponent, like I said. Okay. Obviously, if Cn is 0, then this is not an nth degree polynomial because this term is just 0. So it's not, it might as well not be there, right? And as you may know from high school, a 0 degree polynomial is called a constant polynomial. A first degree polynomial is called a linear polynomial. A second degree is a quadratic. A third degree is a cubic. A fourth degree is a quartic. Then there's a quintic, a sextic, I don't remember the rest. But in any case, we can classify polynomials by their degree, and in high school most of what you worked with were 1 and 2 degree polynomials, linear and quadratic ones. Okay? Now then, a rational function well, I'm sure you've heard this term before too, but just as a reminder, a rational function is a ratio of p of x over q of x, where p and q are polynomials. Okay? So just, and of course, q cannot be the 0 polynomial. So you take any polynomials you like as long as the bottom is not 0, divide them, and then that's a rational function. Okay? Now it turns out that every rational function can be written as a sum of a polynomial and another rational function whose numerator has a smaller degree than its denominator. Let's look at an example here. So for example, we have x squared plus x plus 1, and let's say we divide that by x plus 1. That's a rational function. Now I notice here that the degree of the numerator is 2 and the degree of the denominator is 1. And of course 2 is greater than 1. Now I am saying that I can write this as a polynomial plus a rational function with a degree of the numerator less than the degree of the denominator. I can do it like this. We can say, first of all, that that numerator is x times x plus 1 divided by x plus 1. And from there, that makes it pretty clear that we're dealing with x plus 1 over x plus 1. And now, just as I promised, we have here a polynomial. It's a degree 1 polynomial. And here we have a rational function where the degree of the numerator is 0, and the degree of the denominator is 1. And of course, 0 is less than 1. Okay? So, basically, this means that if you know how to integrate a rational function where the degree of the numerator is less than the degree of the denominator, then you can integrate all rational functions. Because you can always do this. You can always find some way to write it as a polynomial plus something like that. And so this is what we're mostly going to be focused on today. Rational functions where the degree of the numerator is less than the degree of the denominator. Now then, the method of figuring out the antiderivative of a rational function who has a smaller degree numerator than denominator is called, as you hopefully guessed by this point, partial fraction decomposition. Okay? And the idea of this is that you're going to factor the denominator into a bunch of factors, and then you're going to write that fraction, that rational function, as a sum of a bunch of other rational functions that will hopefully be easier to integrate. Okay? So there are 3 cases here. And by the way, these 3 cases do have some overlap. Like, you can have more than one case happening. But in any case, let's just get into them. So case 1. So let's say you have a, right, so let's say before we begin this discussion at all that we're dealing with a rational function. It's named f of x, and its numerator is a polynomial called p of x, and its denominator is a polynomial called q of x. Okay? And once again, q of x is not the 0 polynomial. Okay? So, and yeah, as I said, the degree of p is less than the degree of q. Because if that's not the case, then you cannot do this. So, case 1. The denominator q of x is a product of distinct linear factors. So q of x can be factored into distinct linear polynomials. So let's look at an example of that. So let's say we're trying to evaluate the integral x plus 1 divided by x squared plus x minus 2. Okay. This is a rational function where the degree of the numerator is 1, the degree of the denominator is 2. So let's notice here that this denominator can be factored. It factors into x plus 2, x minus 1. Okay? So what we're looking at here can actually be written as x plus 1 over x plus 2 times x minus 1. Okay? Now then, when you're dealing with this case, case 1, you're going to write this in a different way. You're going to write this as a constant divided by the first factor plus a constant divided by the second factor. And of course, if there are more than 2, then you're going to have more than 2 terms there. And as I just want to emphasize one more time, a and b are constants. They are not dependent on x. Okay? Turns out that we are guaranteed that we will always be able to find these constants. Again, provided the degree of the numerator is less than the degree of the denominator. Okay? So the way we can handle this is like this. What we'll do is we'll multiply both sides by x plus 2 times x minus 1. If you do that, then on the left side the denominator will just cancel. On the right side, there will be some cancellation, but not for the whole thing. So you'll get a times x minus 1 plus b times x plus 2. Okay? And that's because when x plus 2 times x minus 1 multiplies by something over x plus 2, the x plus 2's cancel, so you just get an x minus 1 left, and similarly over here. Okay? Now then, let's distribute this. So let's look at x plus 1 equals ax minus a plus bx plus 2b. All right, now what happens if we combine like terms in powers of x? Well, we could say this is x plus 1 equals a plus b times x plus 2b minus a. All right. Now then, what we are saying is that these two polynomials are equal for every value of x. Except possibly -2 and 1. Whatever. You can't really deal with this when x is 1 or -2 because obviously this doesn't make sense in the first place. But accepting perhaps those two values, these polynomials have to be the same. For every value of x, those two. Okay? If these two polynomials give the same values at every single point, then that means that their coefficients have to be equal. There's no other way that can happen. So that means a plus b has to be the same as 1, because this is 1x over here. And 2b minus a has to be the same as 1, because this is 1 over here. So we get a system of two equations, a plus b equals 1, and meanwhile 2b minus a equals 1 as well. Okay? So I'm just picking off the coefficients of these two polynomials. This is, as I said, this is 1x plus 1. So I'm just saying 1 is a plus b, and 1 is 2b minus a. The linear coefficient is the linear coefficient, and the constant coefficient is the constant coefficient. Simple as that. Alright? Well, now you can solve this system of equations for a and b. Probably the easiest way to do that would just be to add these two equations together, because when you do that, the a's cancel, and then you just get 3b equals 2. So we get 3b equals 2. And then that makes it pretty clear that, wait a second, my notes are contradicting what I'm saying here. Oh, I see why. Yes. The way I set this up in my notes is I had the definition of b as the thing over x plus 2 and a as being the thing over x minus 1. So as a result, my values that I'm going to get here are interchanged with the ones that I actually have in my notes. So that would explain why I'm getting an inconsistency. In any case, the end result will be the same. Now then, b is 2/3, and then in that case, that means a has to be 1/3. Because it has to add up to 1. Alright, so then in that case, what we're looking at here is this rational function can be written as 1/3 over x plus 2 plus 2/3 over x minus 1. So what we're actually dealing with now is the integral of 1/3 over x plus 2 plus 2/3 over x minus 1 dx. Okay. And that happens to be a lot easier to handle. Because of course we can just split this into two integrals. So now we get 1/3 times the integral of 1 over x plus 2 dx plus 2/3 times the integral of 1 over x minus 1 dx. And then you can do a u substitution on each of these individually. You just set u to the denominator of whatever you're dealing with. What you'll get is 1 over u du, and then the antiderivative of that is ln absolute value of u, and then you just replace u with what you define it as, so this becomes 1/3 natural log of the absolute value of x plus 2 plus 2/3 natural log of the absolute value of x minus 1 plus c. Okay? And that is our indefinite integral. Now you might be saying here, can't you just do this by u substitution instead? The answer is no. The answer is no. If you try to say u equals x squared plus x minus 2, then du ends up being 2x plus 1 dx. Alright, well we have 1x up here, but where are you going to get the other x from? Or alternatively, you could say, alright, well I'm just going to divide both sides by 1/2. Fine, but then what are you going to do about this 1? Either way, you run into some trouble if you try to do it by just u substitution, so we need something different. Anyway, that's how it goes for case 1. When you've got the denominator being able to be factored into linear factors that are different from each other, then you just give each of those factors a term, and you just put some constants on the numerators. Okay. Now then, suppose instead of distinct linear factors, we say q of x can be factored into repeating linear factors. let's look at an example. Let's suppose we're trying to evaluate the integral. Let's suppose we're trying to evaluate the indefinite integral of 4x divided by x minus 1 times x squared minus 1 dx. All right, well, our first step is going to have to be to factor the denominator completely. And this is not completely factored because x squared minus 1 can be written as x minus 1 times x plus 1. Then you have x minus 1 times x minus 1 times x plus 1, which is just the same as x minus 1 squared times x plus 1. So what we're actually looking at is 4x divided by x minus 1 squared times x plus 1. Okay. And now this is different from case 1 because x minus 1 is repeating here. These linear factors that we get 3 linear factors here, but they're not what we call distinct. They're not all different from each other. We get 2 of those factors both being x minus 1, and so we have to do something different here. What we do in this case is we just need to say, all right, well, I'm going to give a term to each of these factors, but also I'm going to give an extra term to however many times one of the factors repeats. So I'm going to say this is a divided by x minus 1 plus b divided by x minus 1 squared plus c divided by x plus 1. Okay. So you see, you don't just have a over x minus 1 like we did before. Now you have another one, also devoted to x minus 1, but this one is squared. Okay. And by the way, if we had a cube, if we had 3 as the exponent here, there would be 3 terms devoted to x minus 1. The denominators would look like x minus 1, x minus 2 squared, x minus 2, x minus 1 cubed, respectively. And then if it was to the 4th power, there would be 4 terms, and if it was the 15,000th power, there would be 15,000 terms, and so on. Okay? Anyway, we're going to proceed like we did before. We're going to start by just clearing the denominators, because honestly, it's not nice to work with fractions. They're annoying, right? So let's just clear the denominators by multiplying everything by the bottom of this fraction right here, x minus 1 squared times x plus 1. So on the left-hand side, we'll just get 4x. On the right-hand side, we'll get a times, well, let's see here. One factor of x minus 1 is going to cancel, and then we're going to have one factor left over, and then there's also going to be an x plus 1. Then b and 2 factors of x minus 1 are going to cancel, so we're just going to have b times x plus 1. And then there's c, and let's see, only x plus 1 is going to cancel, so we're going to be left with x minus 1 squared. Now then, once again, we're going to try to distribute. So 4x is going to be the same as a times x squared minus 1 plus b times x plus 1 plus, let's see, c times x squared minus 2x plus 1. Again, we need to distribute a bit more. So 4x equals ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. And then, as before, we will combine like terms in powers of x. So we have 4x. This is going to be equal to, let's see here, we have a plus c times x squared. A plus c times x squared. Then we have bx minus 2cx, so that makes b minus 2c times x. And finally we have b plus c minus a. All right. And all of that has to be 4x, which, by the way, is the same as 0x squared plus 4x plus 0. So this is 0x squared plus 4x plus 0. Okay? And once again, we are claiming that for all values of x, except maybe a few exceptions, which, you know, we're not even going to mention, these two polynomials have the exact same values. That means that they have to have the same coefficients. That means that this quadratic coefficient has to be this quadratic coefficient, and this linear coefficient has to be this linear coefficient, and this constant coefficient has to be this constant coefficient. So we get, again, a system of, well, now it's 3 equations. We get a plus c has to be 0. We get b minus 2c has to be 4. And we get b plus c minus a has to be 0. Okay? And now it's come down to solving this system of 3 equations. Now, let's see here. Of course, there's more than one way to solve a system of equations. We probably talked about it a lot in high school algebra. I don't know what the most expedient method it would be, but I guess the first thing I want to say is that c is equal to negative a, right? Well, then in that case, the second equation becomes b plus 2a equals 4. And meanwhile, the third equation becomes b minus 2a equals 0. Now that we're here, we can add these two equations together, and then the 2a's will cancel. So then we'll just get 2b is equal to 4, which means that b has to be 2. And since b is 2, and since b is 2 and b plus 2a is 4, that would mean that 2a has to be 2, or in other words, a has to be 1. So a is 1, and then since c is negative a, that would mean that c is negative 1. Okay? So this right here, well, now what we're dealing with is the integral of, let's see here, a is 1, so this is 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1 dx. Okay? And that's just putting in a, b, and c for their definitions here and saying that rational function is this decomposition. By the way, I just want to point out, I think I meant to mention this earlier, but I forgot. If you were to find a common denominator between these 3 fractions, you know, these 3 fractions, then it would be the same as that when you add them together. Okay? What we are doing when we do a partial fraction decomposition is we're trying to reverse the process of finding a common denominator. Okay? Which just isn't as easy as maybe you'd hope it would be. And that's why, you know, we're doing this lecture. Once again, you can split this into 3 separate integrals. You have the integral of 1 over x minus 1 dx plus 2 times the integral of 1 over x minus 1 squared dx minus the integral of 1 over x plus 1 dx. Okay? And just like before, you know, these two you can handle by just doing u substitution on u equals x minus 1 or x plus 1, depending on which integral you're talking about. And this one can also be done by a u substitution on u equals x minus 1. Although these two are going to turn into natural logs, whereas this one is going to turn into negative u to the negative 1. And so what this eventually turns into is natural log of the absolute value of x minus 1 plus, or actually minus, 2 divided by x minus 1 minus the natural log of the absolute value of x plus 1 plus c. And that is our indefinite integral. All right. Now then, oh, well that was dumb. I forgot to change that 1 to a 2. This is actually case 2. Yeah, what we just did was case 2. Sorry about that. Repeating linear factors, case 2. Sorry about that. Okay. So that's case 2. Now let's also talk about case 3. The final case. So, case 3 is that q of x contains or is divisible by irreducible quadratic factors. Okay. First of all, I just want to take a moment to remind you what that means, or tell you if it's the first time you're seeing the term irreducible polynomial. An irreducible quadratic is one that you cannot factor over the real numbers. So in other words, if you were to try and find its roots, they would be non-real. Hopefully you dealt in high school with quadratic functions where their roots were non-real complex numbers, right? Yeah, that's what this is talking about. So for example, x squared plus 16. This is an irreducible quadratic because it's not equal to 0 for any real number. Okay? And, just like in high school, if you want to determine whether a quadratic polynomial is irreducible or not, you just have to take b squared minus 4ac, the discriminant, and determine whether that is less than 0. If it's less than 0, it's irreducible. Okay? Like here, for example, b squared minus 4ac would be 0 squared minus 4 times 1 times 16, which is negative 64. Okay? So that shows that this is an irreducible quadratic. Can't factor it any further over the real numbers. Okay? So, let's take a look at an example of one of these. So let's say we have 2x squared minus x plus 4, and we're going to divide that by x cubed plus 4x dx. Okay, so once again, we need to completely factor the denominator as much as possible. So we'll get 2x squared minus x plus 4 divided by x squared plus 4 multiplied by x. And then x squared plus 4 cannot be factored further because it's an irreducible quadratic. Again, b squared minus 4ac is negative. So, At this point, we need to do some kind of partial fraction decomposition on it, and it's going to be a similar thing. It's just now the irreducible quadratic is going to be given its own term, and its numerator is not just going to be a constant, but actually a linear polynomial. So this is actually going to be ax plus b divided by x squared plus 4. And then there will also be a term for the x here, so that's just going to be c over x. Okay? So the irreducible quadratic gets its own term. The numerator is ax plus b and not just a. Right? And then, of course, if we had multiple distinct irreducible quadratics, like if this were like x squared plus 4 times x squared plus 9, for example, then that would deserve its own term as well, and then its numerator would be like cx plus d. Okay? So, just as before, we're going to clear the denominators by just multiplying through by x squared plus 4 times x. So we'll get 2x squared minus x plus 4 is equal to, let's see here, this is going to be ax plus b times x plus c times x squared plus 4. Then, once again, we'd like to distribute everything. So we get 2x squared minus x plus 4 equals, let's see here, this is going to be ax squared plus bx. And this right here is going to be cx squared plus 4c. Now, we're going to combine like terms and powers of x. So this is going to be 2x squared minus x plus 4 equals, let's see here, we have a plus c times x squared plus bx plus 4c. So then, just as before, we're asserting that these two polynomials are the same for all values of x, except maybe a few exceptions. So that means that their coefficients, their corresponding coefficients have to be equal. So what we get here is that a plus c has to be 2. So a plus c equals 2. B has to be negative 1. So b is negative 1. And 4c has to be 4. 4c equals 4. All right. So of course, that leaves no mystery as to what b is. As for c, that makes it pretty clear that c is going to be 1. And then if c is 1, then that means that a has to also be 1. All right. So now, this decomposition becomes, well, what we're dealing with is the integral of, let's see here, 1x minus 1 divided by x squared plus 4 plus 1 over x dx. Okay. Now then, just as before, we can separate this into more than one integral. First of all, we can say this is equal to the integral of x minus 1 over x squared plus 4 dx plus the integral of 1 over x dx. This one is easy to handle. This one is less obvious how to take care of it. Okay. This one, first of all, let's understand that partial fraction decomposition is not going to work on this. Okay. It's not like integration by parts where you do it and then maybe it'll be helpful to do it again. If you do partial fractions again, you're not going to get anything new because this is already in its most decomposed form, so to speak. All right. So we need to find the antiderivative of x minus 1 over x squared plus 4. The easiest way to do that, I think, is to split that into two integrals, to say, first of all, it's going to be x over x squared plus 4 dx minus 1 over x squared plus 4 dx plus 1 over x dx. Okay. Now this can be handled through u substitution. You just set u to be x squared plus 4, and then du becomes 2x dx. You need to do some fiddling with the constant, but it's no problem, right? And this one, you know, it's just going to be ln absolute value of x. What about this one? Well, let's see here. So, first of all, let's do what I said. Let's handle those first two cases. This is going to turn into 1/2 integral of 1 over u du, where u equals x squared plus 4 in this case. And then this one is going to be integral of 1 over x squared plus 4 dx. And then this one, yeah, we already know that's just going to be ln absolute value of x plus c. Fine, whatever. And then that one just becomes ln absolute value of u plus c. But u is x squared plus 4, so then this becomes negative integral of 1 over x squared plus 4 dx plus 1/2 natural log of x squared plus 4 plus natural log of the absolute value of x plus c. So we've done everything except the hardest part. Okay. Now, for this one, there are two ways of handling it. One way is to do it by trigonometric substitution. That totally works. You can set x equal to 2 tangent theta and then go from there, and that totally works. There is another way. It's like this. You see, this function right here, doesn't it look an awful lot like the derivative of arctangent? Well, yeah, but there's a 4 here rather than a 1, right? We can actually handle that. Here's what we'll do. What we'll do is we'll first factor a 4 out of the denominator. So first of all, we're going to say this is negative 1/4 integral of 1 over x squared over 4 plus 1 dx. And then, you know, there's the rest. That's not the hard part, so, you know, we'll just forget that for now. Now then, that looks even more like it, right? But now, this isn't x squared, it's x squared over 4. But that's okay, because x squared over 4 can be understood as x over 2 squared. So this can be understood as negative 1/4 integral of 1 over x over 2 squared plus 1 dx. Now from here we can say u equals x over 2. If we do that, u equals x over 2, then du ends up being 1/2 dx, of course. Running out of space. I guess let's erase this first part. Now, that means that what we're dealing with here now is, let's see here, so dx becomes 2 du, which means that we have now negative 1/2 integral of 1 over u squared plus 1 du. And now that really is the derivative of arctangent, right? So we can go ahead and do that. We can say this is just negative 1/2 arctangent u plus c, and then u is by definition x over 2, so this is negative 1/2 arctangent of x over 2 plus c. Again, that's not the only way you could have done this. You could have done it by trigonometric substitution as well, but it was just one way. Okay. Anyway, we put all this stuff together, and that is our indefinite integral. So that we're going to get 1/2 ln of x squared plus 4 plus ln absolute value of x minus 1/2 arctangent of x over 2 plus c, and then that is it. Okay? So, at this point we've dealt with the possibility that you can have the denominator factoring into a bunch of linear terms that are all different from each other. You could have a bunch of linear terms where there's some repetition. I shouldn't say terms, I should say factors. Linear factors where there's some repetition. And finally, you could have irreducible quadratic factors. So you might be asking, all right, well, could you have a higher degree polynomial that perhaps you can't factor further? Like a degree 3 or 4 or 5 or 100? The answer is no. There is a theorem known as the fundamental theorem of algebra that says that every single polynomial over the real numbers, if it is irreducible, then it must be either quadratic or linear. Linear polynomials, of course, you wouldn't bother to reduce them. But quadratic polynomials, well, those can pop up. Okay? But the fundamental theorem of algebra says there's no such thing as an irreducible cubic polynomial. There's no such thing as an irreducible quartic polynomial. Those can always be factored further. You're always going to get degree 1 and or 2. That's it. Okay? And that means that these three cases completely handle the problem of figuring out the integral of a rational function where the degree of the numerator is less than the degree of the denominator. So let's do some mixed examples now, just to get a bit of practice before you start your homework. Right, so first of all, here's the integral from 0 to 1 of x minus 4 divided by, let's say, x squared minus 5x plus 6 dx. Right, so x minus 4 divided by x squared minus 5x plus 6, well, that is the same as x minus 4 divided by x minus 2 times x minus 3. So we have distinct linear factors here. Case 1. So that means we get that this is going to end up being a over x minus 2 plus b over x minus 3. And as I unintentionally mentioned earlier, if you switch the definitions of a and b, if you say a is over x minus 3 and b is over x minus 2, that's not going to be a problem as long as you're consistent. Okay? You'll get the same end result. Anyway, let's clear the denominators by multiplying everything by this denominator right here. So what we'll get is x minus 4 equals, let's see here, that's going to turn into a times x minus 3 plus b times x minus 2. And of course, we distribute. So we get x minus 4 equals ax minus 3a plus bx minus 2b. Collect like terms and powers of x, and we get x minus 4 equals a plus b times x plus, I guess, negative 3a minus 2b. And so, this indicates that a plus b has to be 1, and negative 3a minus 2b must be negative 4. So, now we have a system of equations that we can solve for a and b. Okay, well, the first thing I notice is that we can cancel the negatives from the second equation. So, I mean, I guess we might as well do that. Actually, though, probably be easier to keep them there and just multiply the first equation by 2. Yeah, so let's say this is going to be 2a plus 2b equals 2. And the bottom equation becomes negative 3a minus 2b equals negative 4. So now if you add these two equations, the b's cancel. And then you just get negative a equals negative 2, which means a has to be 2. And therefore b, let's see, if a plus b is 1, then that means b has to be negative 1. Okay. So, once we have these two coefficients, we know this decomposition, and that means that our integral now becomes, let's see, this is the integral from 0 to 1 of 2 over x minus 2 minus the integral from 0 to 1 of 1 over x minus 3. Okay. And now both of these can be done by u substitution. I'm going to be explicit about this one because it's a definite integral, so we want to make sure we change the bounds correctly. So I'm going to call this first one u1, and it's going to be x minus 2. So du1 is going to be dx. This other one I'm going to call it u2. Anyway, it's going to be x minus 3, and then du2 is dx as well. So then this, and by the way, these bounds change too. When x equals 0, then u1 is negative 2. So this is going to be the integral from negative 2. And then when x is 1, u1 is negative 1. So this is going to be from negative 2 to negative 1 of, let's see, it's going to be 2 divided by 1 over u1 du1. At the same time, we're going to have this one over here, so this is going to be minus the integral of, let's see, when x equals 0, u2 is negative 3. And then when x is 1, u2 is negative 2. So this becomes 1 over u2 du2. Now, you might be wondering, why am I being so careful here with these subscripts? Like, isn't it okay to just put u's here? The answer is yeah, pretty much. As long as you don't try to like put these together, which you won't do if you have the bounds different, then it's fine. It's not really going to be a problem. I just like to be careful. Okay? Anyway, this is going to end up being 2 natural log of the absolute value of u1, evaluated from negative 2 up to negative 1, minus natural log of the absolute value of u2, evaluated from negative 3 up to negative 2. Alright, so then this becomes 2 times natural log of 1 minus natural log of 2 minus, let's see here, this one is going to be natural log of 2 minus natural log of 3. Natural log of 1 happens to be 0. Let's see, then we have, well, I guess this would end up being negative 3 ln2 plus ln3. Did I get that right? Let me just check my notes here. Yep, that's right. I did some more simplification in my notes, but that is our number. Let's try another one. So the next one is going to be an integral of x times 3 minus 5x divided by 3x minus 1 times x minus 1 squared dx. Alright, so now the denominator is already factored for us. That's nice, I suppose. In any case, we have repeated linear terms. So this is going to be case 2. So first of all, we're going to come up with a decomposition. X times 3 minus 5x over 3x minus 1 times x minus 1 squared. This becomes a over 3x minus 1 plus b over x minus 1 plus c over x minus 1 squared. Okay, and again, that's because we have a repeated term here. We need to devote another term. We have a repeated factor here. We need to devote another term to each repetition of that. Okay? So you clear the denominators once again. You get x times 3 minus 5x equals a times x minus 1 squared plus b times 3x minus 1 times x minus 1 plus c times 3x minus 1. Alright, so distribute everything. The left side too. So the left side is going to become minus 5x squared plus 3x. Anyway, this equals there's going to be a times x squared minus 2x plus 1, and then b times 3x squared, let's see, minus 3x minus x, so that makes minus 4x, plus 1, plus c times 3x minus 1. Anyway, this is now negative 5x squared plus 3x plus 0. Let's see here, we've got a plus 3b times x squared plus, let's see here, we have negative 2a minus 4b plus 3c times x, so negative 2a minus 4b plus 3c times x, and then a plus b minus c. So a plus b minus c. Alright. Right, so now, as usual, we can say these two polynomials are the same for all values of x, exceptions. And then that means the coefficients have to be equal. So that means a plus 3b has to be negative 5. And then negative 2a minus 4b plus 3c has to be 3. And a plus b minus c has to be 0. Alright, so I guess the way I want to handle this now is by saying, okay, by the last equation, c has to be a plus b. So the last equation indicates that c is just a plus b. And then in that case, the second equation really says negative 2a minus 4b plus 3 times a plus b equals 3, which, of course, can be simplified a bit. We can turn that into a minus 3b equals 3. And what do you know? We have a plus 3b equals negative 5. a plus 3b equals negative 5. And then, of course, you can add these two together, and what you get then is 2a equals negative 2, which means a has to be negative 1. Now, if a is negative 1, then you can solve this equation for b. You're going to get, let's see here, you're going to get 3b equals negative 4, so therefore b equals negative 4/3, is that right? No, doesn't look like it. All right, need to be more careful here. So, let's see, we got so you add these two together, you get negative 2. C equals a plus b. Let's see, a. Oh, of course, yeah. Yeah, I did mess that up. So this is going to be a minus 4b plus 3b, which is just going to be minus b. So a minus b actually equals 3. And then in that case, what we're looking at here is a plus 3b equals negative 5. Alright, that's more like it. So now we can subtract this equation minus this one, and then what we'll get is 4b equals, I guess, negative 8, which means b equals negative 2. And then if b is negative 2, then a is going to end up being, let's see here, 1. And then c, which is a plus b, has to be negative 1. Okay? Now then, that means that what we're dealing with here is now the integral of, let's see here, we have 1 over 3x minus 1 dx, then minus 2 integral of 1 over x minus 1 dx, and then minus 1 integral of 1 over x minus 1 squared dx. Okay? Now then, each of these can be done by u substitution. This first one, we would say u equals 3x minus 1, then du becomes 3 dx. Over here we would say u equals x minus 1, then du becomes dx. And over here we would say u equals x minus 1, and then du becomes dx. And yes, this time I'm being sloppy. This time I'm calling them all u, even though I mean different things by them. But as long as we don't try to put the integrals together, that's fine. It's not going to harm us in any way. So this is going to become 1/3 integral of 1 over u du. This is going to become minus 2 integral of 1 over u du. And this one is going to become minus integral of u to the negative 2 du. Now this one becomes just 1/3 natural log of the absolute value of 3x minus 1 minus 2 times the natural log of the absolute value of x minus 1 minus 1 over, actually plus 1 over x minus 1 plus c. And if I didn't make a mistake here, or at least another mistake, then that should be our answer. Yeah, looks like it. Okay. let's do another for case 3. So this one is going to be x cubed plus 6x minus 2 divided by x to the 4th plus 6x squared dx. Okay. Now this one, all right, let's factor this one, the denominator at least. So we're going to get x cubed plus 6x minus 2 divided by x squared times x squared plus 6. This is an irreducible quadratic. Again, b squared minus 4ac is less than 0. This one, x, is a linear polynomial, but it's repeated. X minus 0 squared, right? So this is a kind of hybrid of cases 2 and 3. Like I said, they could happen more than, you could have more than one case at a time. Okay? So the way we handle this is, well, we're going to have a over x plus b over x squared. And that's going to handle the x squared part of the denominator. Then we're also going to have cx plus d divided by x squared plus 6, and that handles the x squared plus 6 part of the denominator. Okay? So you see, when you have one of these hybrids, you just need to deal with each kind of factor individually. Okay? You just need to put in as many terms as you need for that factor, and then add them all up. Anyway, we multiply by the denominator here, we get x cubed plus 6x minus 2 equals, let's see here, this is going to be a times x squared plus 6 plus b times x squared plus 6 plus cx plus d times x squared. Now then, let's distribute. So we'll get x cubed plus 6x minus 2 equals, let's see here, this is now ax cubed plus 6ax plus bx squared plus 6b plus cx cubed plus dx squared. We combine like terms in powers of x. So now x cubed plus 0x squared plus 6x minus 2 equals, let's see here, we have a plus c times x cubed plus b plus d times x squared plus 6ax plus 6b. And then, as usual, corresponding coefficients are equal. So that means a plus c has to be 1, b plus d has to be 0, 6a has to be 6, and 6b has to be negative 2. Then that makes it pretty clear that a is 1. So a is 1. Also, b is negative 1/3. Then, a plus c equals 1. Well, then in that case, c has to be 0. And then b plus d equals 0. That means that d has to be 1/3. So, this now becomes the integral of, let's see here, we have a, which is 1 over x, then b, which is negative 1/3 over x squared, then c is 0, and then d is 1/3, so we're going to have plus 1/3 x squared plus 6 dx. Okay? And so now, again, we can split this into 3 separate integrals that we can do individually. 1 over x dx minus 1 over 3 integral of x to the negative 2 dx plus 1 over 3 integral of 1 over x squared plus 6 dx. Alright, and so now this first one is just natural log of the absolute value of x. The second one, let's see, you're gonna get plus 1 over 3x. And then there's this last one, which again is this weird thing that kind of looks like the derivative of arctangent, but not quite. Okay. And once again, you can do it by trigonometric substitution. You can just say x equals the square root of 6 times tangent theta, and do it like that. I'm going to choose to, again, do the u substitution to figure this out using the derivative of arctangent. So first of all, I'm going to factor out a 6 from the denominator. So 3 times 6 is going to be 18. So 1 over 18 integral of 1 over, right, it's going to be x squared over 6. Well, that's the same as x over root 6 squared. So I can write that. X over root 6 squared plus 1 dx. And again, u equals x over root 6, and then du equals 1 over root 6 dx. From here, this becomes, well, the first terms stay the same. Natural log of the absolute value of x plus 1 over 3x. Then this part, let's see, 18 is 6 times 3, so this becomes 1 over 3 root 6. Yeah, I guess so. So 1 over 3 root 6, although now I think about it, yeah. 3 root 6 times the integral of 1 over u squared plus 1 du. And once again, that's just the derivative of our tangent right there, so we can just do the antiderivative. This becomes natural log of the absolute value of x plus 1 over 3x plus 1 over 3 root 6 arctangent of u. In our case, u is x over root 6. And then there's a plus c. So, that becomes our indefinite integral. Yeah, it looks like in my notes I went ahead and rationalized this denominator, multiplied top and bottom by root 6, but of course it's the same. Alright, let's do one more. Just one more so that we can really get the idea of what happens if you don't have the degree of the numerator being less than the degree of the denominator. So yes, what happens if you take away this condition? Alright, let's take a look at that. So this one is going to be x to the 5th minus 7x cubed plus 6x minus 2. And all of that is going to be divided by x to the 4th plus 6x squared dx. Well, as I said at the beginning of the lecture, you can find a polynomial and a rational function with a numerator degree less than its denominator degree, and add them together and get this. Okay? But I didn't say how you could do that. The way that you do that is with polynomial division, or synthetic division as it's sometimes called. Anyway, you probably learned it in pre-calculus and then immediately forgot it. At least that was my experience. So here's how it goes, just to remind you. We're going to try to divide x to the fourth plus 6x squared into x to the fifth plus 0x to the fourth minus 7x cubed plus 0x squared plus 6x minus 2. So here's how it works. We just say, how many times does x to the fourth go into x to the fifth? Well, x many times. Depends on what x is. So, we get x there. We multiply through, just like in regular old long division. You multiply through and you get x to the fifth plus 6x cubed. So I guess that's plus 0x to the fourth plus 6x cubed. Wait a second. Oh. Huh. I don't know what I was thinking here. This should be a plus sign. Really doesn't change much. It's not like the problem would be broken without it. It's just, yeah, I just made a mistake there. Anyway, so now, just like in regular old long division, we're going to subtract this off. And remember the parentheses. Those are important because, you know, negative signs distribute and all that. So x to the fifth minus x to the fifth is 0. 0x to the fourth minus 0x to the fourth is 0. 7x cubed minus 6x cubed is 1x cubed. So we get x cubed. All right. And now at this point we might ask, well, how many times does x to the fourth plus 6x, or yeah, how many times does x to the fourth go into x cubed? Well, it doesn't. Which is fine, because x cubed has a smaller degree than x to the fourth. So, at this point, you bring down this part. You bring down 0x squared plus 6x minus 2. And then that is your remainder. Now then, what this is saying, what this is all saying, is that that numerator can be written like this. That numerator there is the same as x to the fourth plus 6x squared times x. So let's put that in. X to the fourth plus 6x squared times x plus this remainder. So that would be x cubed plus 6x minus 2. Anyway, this is still over x to the fourth plus 6x squared. Now, these two will cancel, right? I mean, you still have to divide this, but there's some cancellation happening. So this becomes the integral of x plus x cubed plus 6x minus 2 divided by x to the fourth plus 6x squared dx. And now, you can, of course, split this into two integrals. You have the integral of x dx plus the integral of x cubed plus 6x minus 2 over x to the fourth plus 6x squared dx. And then this one, as you can see, has a numerator with a degree smaller than the degree of its denominator. And so you can do partial fractions on this. Okay? Thankfully, we already did that because that was the previous example. So that's how you do it. You reduce it to a problem that we can handle by just doing synthetic division to put it into the form that you can use partial fractions on. Okay? So, homework is up. Go ahead and get some practice on that.